Hi, in this video, we want to take a look at interval estimation for linear regression, and we want to take a look at hypothesis testing on correlation. All right, so for interval estimation, what we want to do, we want to get a confidence interval on the slope and the intercept of our simple linear regression model. Okay, so first thing that we need to do, we need to remember what is the formula for linear regression. We're going to say that the expected value of our dependent variable given our independent variable, so the expected value of y given x, is going to be equal to a, the little a here that we have, plus b times x, and that's our expected value. All right, now our formula is that y is equal to a plus b times x plus a term that accounts for the randomness, the other variables that we are not accounting for in our model. All right, so for us to be able to do interval estimation, I'm going to need a measurement of the variance standard deviation on my estimate of the slope and the y-intercept. Okay, so we're going to get our standard error. And for the slope, here's our formula for the standard error. And here is our formula for the standard error of the y-intercept. Okay, and so using this, our point estimates and our knowledge of what the corresponding distribution for the slope and the intercept as random variables from the data that we're collecting, assuming the whole random hypothesis things, we can get our interval estimation. All right, so remember, anytime I have interval estimation, I have the point estimate, I have plus or minus a term for the distribution, and then I have the standard error. Okay, so here's that formula. Here is our point estimate of the slope, time plus or minus t. So what this is telling us is that under the hypotheses of simple linear regression using normal errors, independent, identically distributed, constant with respect to y is constant distribution with respect to x, given x. We're going to get a t distribution on the slope, and then the standard error of b, which is up here. If we were to do the pencil and paper calculations to work this out, if you look at my videos on linear models, I go over exactly how to derive this. Now here is for the intercept, our point estimate. Once again, t distribution, so plus or minus t, times that standard error, which we've got up here. All right, so now we've got, a confidence interval for what is the true slope, the true y-intercept. All right, so now we want to go into a different realm. So frequently, I'm not really interested in the y-intercept. I'm not interested in the slope. I'm interested in the modeled values. For some projects, I'll be interested in the parameters. Some other projects, I'm going to be interested in the modeled y value. So now what I want to do, I want to get a standard error for my modeled y values. Okay, so the standard error is a little bit more complicated on this one. So start deep inside is that we're going to do x minus x bar squared divided by lxx, then plus 1 over n plus 1, all of that times y sub s sub yx squared, then that square root. And that'll be our standard error of y hat. And so now, once I have my standard error of y hat, I can take my point estimation and the distribution of y hat along with standard error, and I get my confidence interval. It's the same game over and over and over when I'm doing confidence intervals. So I take my point estimate plus or minus the distribution. So it's going to be a t distribution for the modeled y values, and then that standard error that we just took a look at. Easy peasy, lemon squeezy. And so what this does, this gives us a standard error around our modeled values. And remember that this is our expected value of y, or our modeled expected value of y, given I know what the x value is. All right, so now what we want to do, we're going to look at the standard error and confidence intervals for predictions made from regression lines with the average value y of the given x. All right, okay, this is actually backwards. Oh, hey, there is a mistake here. All right, so if I look here, this is the prediction interval standard error. So what this does, this interval that I'm going to get from down here, this gives me a realistic range of values that I should see for y. If I see a y value outside of that interval, that's an indication that there might be something wrong. Maybe I have a bad model. Maybe I have a bad data point. Maybe there was a fluke. Maybe there was an error made in data collection. This is the realistic range of what I can see for data for my y values given that particular x. Notice that the standard error increases the farther away my x value gets from x bar. Now here, notice that these are very similar to each other. I'm going to hop back and forth for a second. You see the difference? There's just a 1 right there. There's no 1. Otherwise, it's the same formula. All right, so now, because of that 1, the prediction interval is going to be wider. All right, now, that is for the range of realistic observations. What's happening here without that 1 being there? This is for my this is for the confidence interval for what is the true average. So this standard error is for the range of values I can expect to see for, when I know the x value. This is the confidence. This is for the confidence interval of the true average for a given x value that I know. And something that is important to point out and realize is that anytime I'm doing simple linear regression, the farther away my predictor variable is away from the average of the predictor variables, the more spread out things are going to be. And when it's more spread out, there's more standard error, more uncertainty of what's going on. All right, so now what we're going to need to do, we're going to need to assess the goodness of fit of our regression lines. All right, so the absolute most important way to check your model is to do the visualizations. So if you plot a linear model in R, you'll have 6 options. By default, only 4 will show. If you put which equals 1 to 6, it'll show you 6 of them. I always do that for my professional work. Your scatter plots, hands down, is your most important plot. Your most important plot is to plot the observed values and your y hat values. If they look like they agree well, that's a sign you have a good model. You could be overfitting, but not likely with simple linear regression. But your visualizations are absolutely your most important way of checking model quality. Now, you'll find like in a lot of research papers, a lot of times they want to see particular statistics. Why do they want particular statistics? Because they want something that is just like easier to compare between models. So whatever they want, give it to them. There are tons and tons and tons of ways to assess goodness of fit of regression lines. The most important one is the scatter plots. All right, so if I look at the scatter plot, so here's the predicted value down here. Here is the residual. All right, when I look at my residuals, I don't want to see a pattern. If I see a pattern, I know that I have a bad model. Now, it doesn't mean I won't use it. I need to know the failings and shortcomings if I'm going to launch a model. All right, so here, here's the predicted value. Here are the residuals. And I don't see a pattern here. This looks like a cloud. So this indicates to me that this is a good model. Now, they went ahead and labeled 2 of the points as a 2, the rest are 1s. And so if I was to see a pattern within a particular group of numbers, that would indicate that there is a subpopulation aspect going on in my data. I don't see that here. 2 data points is not enough to pick up anything. So, I'll leave it as is. Now, when you look at these plots, a good rule of thumb, if you're like, do I see a pattern? And you're unsure, you don't know, you're trying to figure out, do I see a pattern? Take any one point and move it, like in your mind, pick it up and move it to another part. If moving one point changes your interpretation of the plot, you don't see a pattern. Similarly, if I was to add a point anywhere on the plot and it would disrupt the pattern I believe I see, I don't see a pattern. If I was to remove one point and that would disrupt the pattern that I thought I saw, I don't have a pattern. Humans are really good at finding patterns that aren't actually there. So always kind of just understand that about yourself. It's human nature. And when you see that, do the 1 point trick. Move something around, delete a point, add a point mentally in your head as you look at the plot. And if your interpretation changes, you don't have a pattern. All right, so now we want to look at the residuals themselves. All right, so now the residual is the difference between our observed data and our modeled value. And so once again, if I want to, we're going to try. So analyzing residuals is a huge part of understanding model quality. And so here is our formula. You'll notice it looks very, very, very similar to what we looked at before. It is a little bit different. Now, studentized residuals. This is a standardized version of residuals. Okay, so there are three major types of residuals. There's raw residuals, which is the difference between my model and my observed data. There's standardized residuals, which is the difference between my model and my observed value minus the mean of the residuals divided by the standard deviation of the residuals. So that will have a mean 0 and standard deviation of 1. Sometimes people don't subtract off the mean. Do whatever works for your project. Now the last one is studentized. And studentized, so first and foremost, when you're doing linear regression, your residuals will always add up to 0. So the mean will be equal to 0. You don't have to worry about subtracting off the mean. Studentized residuals are similar to what I just talked about of the standardized version, but we're tweaking. We're just doing a little tweak on that division by standard deviation. So there's going to be a little bit of them. It's a little bit different than what's here. Sorry, this is what we're going to divide by, which is a little bit different than divide by the residual standard deviation. It's not a huge difference, but there is a difference. Why do we do this? It works out if you take a statistical theory course and you work out the pencil and paper details about it, is that studentized residuals just have more theoretical niceness. They're easier to interpret. We know the probability distribution. Like a lot of sweet, nice, good things happen when we're studentized instead of standardized. Now, studentized residuals only applies in very specific situations when I'm dealing with very well understood theoretical structures of my modeling. So if I'm only interested in theoretical aspects, studentized is awesome. It's amazing. It's great. The downside is if I'm doing something like machine learning, I won't be able to compare my machine learning residuals to my linear regression residuals if I'm using studentized. So usually, I personally use standardized or just raw residuals depending on my project. All right, so frequently we'll do transformations on our data to get better fitting models. Frequently, the square root transform and the log transform are the two that we'll use the most. Also, we could use Box-Cox or Yo-Johnson. Square root transform, if I'm working with count data, look for the square root transform to be a good choice. If I'm dealing with highly skewed data, highly skewed right, that is, look to use the log transform. And the Box-Cox transformation is a good one in whenever I have positive values in my data. All right, so here is the predicted value. Here is the student eyes. And so student eyes, I can interpret these values as being on standard normal distribution. I don't see anything out too far. You know, I'm going to have a most extreme, or a largest and a most negative value whenever I do this every single time. So I know that having something pushing 2, something pushing negative 2.5, it's not that big of a deal. You know, I didn't see a negative 5. I didn't see a positive 10 as a residual. I see something that big, that's an indication there's a problem with that data point for my model. So here, I interpret this as the same way I would interpret standard normal. All right, so now let's go ahead and start talking about correlation. All right, so we're going to talk about Pearson correlation. This is straight line correlation. There are other types. So we've got Pearson correlation, straight line correlation. We have Spearman's correlation, which is rank correlation. And then we have Kendall's tau, which is correspondence. All three have uses and advantages and disadvantages. Pearson's is the best one to use if you're interested in a straight line. That is, we're talking about simple linear regression or regular linear regression, multiple linear regression. All right, and so the correlation coefficient for Pearson is just going to be the covariance divided by the square root of the x sum of squares and the y sum of squares, multiplied together underneath a square root. All right, now these values, the correlation is always between -1 and 1. All right, so if I have a negative value, that indicates that on average, I have a negative slope, for my model. So as x increases, I would expect y to decrease on average. If it's positive, we will expect to see a positive rate of change. So then as x increases, we would expect y to increase. Now, if the number is close to 0, that means that there is a weaker relationship, and close to plus or minus 1 means we have a strong relationship between them. All right, and there's several ways to write the formula for correlation in different projects. If you're doing pencil and paper theory, different presentations have advantages and disadvantages. If I'm, working on a research paper, if I'm doing theoretical statistics, the different formulas lend themselves to different goals. And so all these different formulas that we're going to see in these slides have advantages and disadvantages. Usually in practice, we just get the number and we compare it, between -1, 1, and 0 to interpret what's going on. All right, now what is the relationship between slope of simple linear regression and correlation? Well, it ends up that the slope of simple linear regression is equal to the correlation times s sub y divided by s sub x. And how do we get that? Is that if I multiply r by the square root of L YY divided by L XX, we just do a little bit of manipulation, convert this R to its formula and, do a little bit of tweaks here and there. We end up getting this, which is equal to B. All right, so so the correlation is always proportional to the slope, is the punchline of that. If one is negative, the other is negative. If one is positive, the other is positive. All right, so now let's talk about hypothesis testing on correlation. This works out the same way as every other type of hypothesis testing, that I have a null hypothesis. So here we're going to start with equal to 0. We have an alternative of not equal to 0, and then we get a test statistic. It works out that we're going to be using the t-distribution once again for this. And once I have my hypotheses, I have my distribution, I have my test statistic, I can just go, I can compute my p-value, boom, get it going and rock this. All right, and so here it's just showing t-distribution. If I'm doing alternative of not equal, it's here. If alternative is that the correlation is greater than a particular value, correlation is less than a particular value, we can use each of these. And so here is our formula for our test statistic. And you can see that it's R divided by square root 1 minus R squared times n minus 2. So what this shows us is that it's a combination of the strength of my correlation and sample size. You'll notice that even if I have a very, 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 very small correlation, but I have a huge, huge, huge sample size, I'm going to get statistically significant, even if the correlation is junk. Now, if I was to go through and draw this, you'll notice that I'll have vertical asymptotes close to R equals plus or minus 1. And that's important for understanding like the fact that as I get close to plus or minus 1, this test statistic is going to skyrocket up. All right, so we can also do a test. So using a z transformation. So what we do is I take 1 plus r divided by 1 minus r, take the natural log. So notice that when r is close to -1, that's going to be close to 0. 0 for natural log is like super far low vertical asymptote. Notice that when r is close to 1, I have a vertical asymptote also. And so this will be approximately normal distribution. And here is the mean of the normal distribution. And here is the variance. Notice that the variance, it will go to 0 as my sample size increases. And so here, notice that in this, I'm using the hypothesized value, my null hypothesis value for the correlation. And if my hypothesis, my null hypothesis is that correlation is equal to 0, well, I get 1 on top of 1, natural log is equal to 0. So we'll have normal distribution centered on 0, and the variance will be super small if I have a large sample size. And then we just do exactly the same thing that we've done every single time for this, for hypothesis testing. And here's the one-sided test rejection regions. And of course, I can get confidence intervals. Now, this is going to be a confidence interval on the transformation, so it's going to be a little bit harder to go back and forth, but we can go through and do some calculations, pencil and paper, and get a crosswalk between if we want. So we've got 2 different ways to run correlation hypothesis testing. Do whichever one works for your project, for your stakeholders, which ones they're more interested in. All right, and so if I have not collected my data yet, I have control over sample size. One thing that I could do is I would go, hey, I want to know what sample size do I need to be able to get a certain level of power. And so if I know the power I want, I know my type 1 error risk tolerance, I know my type 2 error risk tolerance, and I've got my hypothesized values, I can go ahead and compute this, and this will give me the minimum sample size needed to achieve the power with the type 1 error risk tolerance I'm willing to accept, the type 2 error risk tolerance I'm willing to accept. If I get a big enough sample size, I can get my power up without having to compromise my error risk tolerance. Now, if we want to do a 2-sample correlation aspect, if I want to check to see if 2 populations will have the same correlation with, so if I have 2 predictor variables and 1 target, I want to see, hey, do these have equal correlation to each other? I can run hypothesis testing. Once again, I'm using the fact that I've normally distributed 2 independent samples. We're going to assume independence and independent variance and just run our calculation just like I would when we were doing the t-tests. Now I need to have a decent sample size to be doing this one, by the way. because otherwise the standard normal distribution would not be applicable. All right, that's all I've got for you. Take care and goodbye.